So we're going to analyze spectroscopic data in order to determine the composition of matter. In other words, what it's made of, what it's composed of. By looking at the light released by these different elements, we can see what they're made of. Okay? So, looks like you need to get out your highlighter, Your electronic highlighter right there. Yeah. All right. So, when we go to a fireworks show, there's all this oohing and ahhing and whoa, right? Well, you've probably experienced the beauty and excitement of a fireworks display, but have you ever wondered how they make those different shapes and colors? How do they do that? What is involved? Would you like that job? Designing new fireworks? Setting off the fireworks? How'd you like to have that job where here at the lake, you go out on the float and you set up all of those mortars and then you light them off, right? Maybe you'd like that, maybe you wouldn't. Some people are kind of pyromaniacs. What does pyro mean? It means fire, yeah. So, have you ever wondered how they make these different shapes and colors? Well, this is just one example of where physics meets chemistry. The following is an excerpt from Wikipedia's entry about fireworks. Okay, so highlight the important text as we go. Fireworks were originally invented in China. Cultural events and festivities, such as the Chinese New Year and the Mid-Autumn Moon Festival, were, and still are, times when fireworks are guaranteed sights. China is the largest manufacturer and exporter of fireworks in the world. The earliest fireworks came from China during the Song Dynasty between 960 and 1279. Fireworks were used to accompany many festivities. The art and science of firework making has developed into an independent profession. In China, pyrotechnicians were respected for their knowledge of complex techniques in mounting fireworks displays. There's that word pyro again, A pyrotechnician is a technician of fire. In regards to colored fireworks, this was derived and developed from earlier Chinese application of chemical substances to create colored smoke and fire, possibly during the Han Dynasty. Such application appears in 14th century writings, which describe recipes using low nitrate gunpowder to create military signal smokes with various colors. So they might be having a battle, and they might make some red smoke or some green smoke or some orange smoke. And those different colors of smoke, first they could be seen far away, And that would be a signal that was almost instantaneous to their troops of what they should do. Later recipes from the 1700s include other chemical substances to tint flames and smoke. So now we're not only tinting the smoke, we're adding color to the flames. These included arsenical sulfide for yellow, copper acetate for green, lead carbonate for lilac white, and mercurous chloride for white. The Chinese pyrotechnics were described by the French author Antoine Callot in 1818. It is certain that the variety of colors which the Chinese have the secret of giving to flame is the greatest mystery of their fireworks. The English geographer Sir John Barlow, around 1797, have you ever seen that little abbreviation before, CA, when it's next to a date? In Latin, you say circa, which means approximately or around or about the time of. So this means about 1797. He wrote, "The diversity of colors indeed with which the Chinese have the secret of clothing fire seems to be the chief merit of their pyrotechny." Suppose I should have put on an English accent for that one. Fireworks were produced in Europe by the 14th century. becoming popular by the 17th century. Berthollet in 1786 discovered that oxidations with potassium chlorate, are we talking about chemistry now? An oxidation is a chemical reaction between something and oxygen. You're doing that right now in your cells to get energy. The food that you just ate, you are oxidizing it to get energy. When you burn gasoline, you oxidize it to release the energy. So are we seeing kind of a overlap between physics and chemistry here? At any rate, he discovered that oxidations with potassium chlorate resulted in a violet emission. Subsequent developments revealed that oxidations with the chlorates of barium, strontium, copper, and sodium result in intense emission of bright colors. The isolation of metallic magnesium and aluminum marked another breakthrough, as these metals burn with an intense silvery light. So magnesium, if you get a pure piece of magnesium, and especially if they make it into a really thin ribbon, like imagine a ribbon of foil, but it's not aluminum foil, it's magnesium foil. You can light it on fire, and it burns incredibly bright. In fact, it's so bright that it can damage your eyes, and they don't let us do that demonstration in class anymore. But imagine a metal that burns, right? Most of the metals we use, we don't want them to burn, do we? So we choose metals that are not going to burn, but magnesium will burn. Modern colored fireworks were invented in Europe in the 1830s. Modern skyrocket fireworks have been made since the early 20th century. So now what I'd like you to do is just take a couple minutes to complete this table. What you're going to do is go back through the reading, and I would skim if I was you, which means you look through the words really fast, right? You skim through the words, you're looking for arsenical sulfide first of all, and all you have to do is write down what color it produces when it's burned. All right? Then you skim for copper acetate and look for its color. So go ahead and do that. Yeah. I think they're in another paragraph. I think the first four are in one paragraph, and then the last ones are at the bottom. I think they're in here. Give me a thumbs up at home when you're done. And you can do that in here too, with for real. Give me a flesh and bone phone.
Third and fifth. I don't know. Oh, and violet emission. For the first one, the violet emission.
Right after indigo? Yeah, it's right there. Potassium chlorate.
Violet emission.
All right, so if you're having trouble finding the last two, they're in the final paragraph. In fact, if you look at the very top of what I have exposed on the screen right now, you'll see potassium chlorate. Yes, sir. Okay, I just don't want you to miss out on the fun. Are we good over here? You got them all? Good back there? Yeah? Excellent. Okay, let's move on. So there is a classic experiment that we are about to do in here, which is called a flame test. Okay? So yeah, we are gonna light up some fire here. And we're gonna do some pyrotechnics. Yes, we are gonna turn off the lights. But before we dive into that, let's look at the introductory information. And once again, you're going to highlight the important text as we go. Yes, sir. I am going to set stuff on fire. I'm going to set stuff on fire. I'm going to set, when you go home, you can set stuff on fire. I take no responsibility for it. Okay, here we go. When elements are strongly heated, they produce different colored flames. These colors have a specific wavelength and frequency that are unique for each element. Once again, do you see how we're overlapping between chemistry and physics here? We're looking at the wavelength and frequency, which is physics, of different elements, which is chemistry. We'll discuss the details later because, well, you may remember that each atom has electrons orbiting around its nucleus. Remember that? Every atom has a nucleus in the center, and there's electrons orbiting around it, huh? All right? So think about that. An electron can absorb energy when it's heated. And when that happens, we say the electron is excited. That's actually a scientific term when we say, oh, it has an excited electron. So here's this electron orbiting the nucleus, and look how far it is from my hand. When it absorbs energy, it goes up here. It's excited. But eventually, it's going to release that energy and fall back down to that more relaxed place. That make sense? When it falls back down to that more relaxed position, it releases the energy it absorbed in the form of light. With me? See, if you were really thinking scientifically a minute ago, when you filled out that chart about what colors are produced by different materials, you were asking in your mind, well, why does this one make violet? Why does this one make red? Why? And how? That's where science is in two words. Why and how? Right? So we call this atom excited when the electron absorbs energy. Later, when the electron loses this energy, it emits a photon, which is a particle of light. The photon behaves like a wave and travels at the speed of light, the fastest thing in the universe. If the photon is traveling with a wavelength and frequency within the visible light spectrum, we can see that color. Now, it might be that an element releases a photon of light outside of the visible spectrum and we couldn't see it, could we? But we have designed machinery called spectrographs that could measure that. Does that make sense? This is why these things give off different colors. They absorb energy. The electron gets excited, and when it calms back down again, it releases light. It releases the energy. It gains energy, and then it releases energy. The release of energy is the light that we see. In this demonstration, you will observe the color of light that is emitted when different metals are heated. You will estimate the wavelength of this light, and you'll calculate the frequency of the light waves. If there's time, you'll also try to identify unknown metals just by looking at the colors they produce. Fill in the data table as you make your observations. Report wavelength in nanometers and frequency in terahertz. So, let's have a look at this data table. So to start with, I'm going to tell you what material it is that we're going to heat up, and I'm going to give you its chemical formula. Just like water is H2O, these have chemical formulas. Then you can see these wooden sticks that are soaking in these different liquids. I'm going to hold the wooden stick in the flame. We're going to turn off the lights, and you're going to write down the color of the flame. After that, you're going to use this chart to figure out about what its wavelength was. Once you've done that, we're going to do some math to find its frequency. Because we are actually high school students now. But first of all, we got to be safe. Help yourself. There you go. And I need some help. It looks like Sawyer, if there's any trouble, you are in charge of the fire extinguisher.
Why would you trust me?
And if there's any trouble, you are in charge of the fire blanket.
Why would you
Safety goggles for chemistry, but they're pretty cool ones, aren't they? They're better than the old school goggles, I think. Yeah, they're kind of retro in a way. If they're too loose or too tight, you can adjust the band in the back, right? There we go. And
We're like this.
I'm going to
We're like this. Hey, yo.
okay, so there's at home. I'm hoping you're going to be able to see this
You're
too.
gonna bring your iPad.
Trying to get the angle right. No, I think we're good. This is going to be good. All right, so let's go ahead and we flip off those lights there. You can't be sitting there if you don't have your goggles in, buddy. You need to trade in for a different pair.
No, I got it. I know.
Yes. So I've turned on the gas, and I'm going to try to spark it. There it is. And I don't know if you've ever worked with a Bunsen burner like this before, but it has two adjustments. One, I can adjust the amount of gas coming through. So I'm changing that. Two, I can change the amount of oxygen coming through. See how it changes from a yellow to a blue flame? My goal is to get it a small blue flame. That's not bad, huh? Okay. And I thought for comparison purposes, and you should move to where you can see, for comparison's purposes, I'm just going to take a wooden splint and let it catch fire. That's just the color of wood burning, which looks like the color that I normally see when I burn wood, doesn't it? Yeah? Just so you can see. So, our first material is called lithium chloride. So what I would like you guys to do is we'll write down the full words in a minute, but let's just put down the chemical formula, which is capital L, little I. This is in the formula column, capital L, little I, capital C, little L. We'll always start an element with a capital. Sometimes it only has one letter. If it has two letters, it's always capital small. So it should be LICL, but capital L, little I, capital C, little L. That was the formula, and we'll come back and fill in the full names in a minute. Okay, so I'm about to take another wooden splint that's been soaking in lithium chloride for about an hour. Okay, and I want you to watch what color it produces when I hold it in the flame. The goal is to avoid having the wood catch fire and just kind of heat up the liquid that's absorbed into the wood. So, are you ready? Okay, here we go. What color do you see?
Blue.
What color do you see coming off of the top, off of the wood?
Blue.
Isn't that incredible? Okay, so we got that lovely red hue from lithium chloride. Pretty ruby red, huh? From lithium chloride. Next, sodium chloride. And that is NaCl. Capital N, little a, capital C, little L.
Say that again.
NaCl with a capital N and a capital C. This is just salt. This is just table salt. Are you ready? Sodium chloride. Move so you can see. Cover your eyes, buddy, especially here in the front row. What color do we get? Okay. So you indicate what sodium chloride gave us. That one's hard to tell the difference between it and the actual flame of the wood, isn't it? Pretty similar yellow-orange color. Next is potassium chloride, KCl. Capital K, capital C, little L. Potassium chloride. Some of these names come from Latin or Greek. Please cover your eyes, buddy. So potassium chloride. Are you ready? What color do you see there? Yeah, it's kind of a pale purple, huh? A lilac, a violet, pale purple. I don't know how well you can see this at home. I hope you can. That was KCl, potassium chloride. KCl, capital K, capital C, little L. Yeah, when I turn on the lights. Right now, just write down the formulas and we'll fill in the full names in a minute. Next, strontium chloride. SR, do you need to trade for a different pair? SRCl for this one, strontium chloride. No, capital S, capital C. SRCl, they're all going to be chloride. And some of them, let me see. Okay, some of them I haven't given you the full name. Let me see which ones. Just this one. It's actually SRCl2 because there's two chlorides, two chlorine atoms attached to a strontium. SRCl2. Are you ready for that? For the strontium? Here we go. What color do we get? Is it the same red as the other one? I feel like it's a little red-orange in there. Next, we have copper chloride. CuCl2. Cu. Capital C, little u. In Latin, copper is cuprum, which is why we're using Cu. CuCl2. Copper chloride. You ready? Here we go. Copper. Yeah? Pretty green, huh?
I heard like what is this type of liberty like copper like bronze or whatever and then it's
Yeah.
green over the
Bronze includes copper combined with tin. And the copper, when it oxidizes, when it rusts, it turns green. Iron, when it rusts, of course, turns reddish. Huh? Next, we have barium chloride, BaCl2. Capital B, capital C. Barium chloride, BaCl2. Okay, here we go with the barium. What do we get there?
Oh, yellow.
Yellow. It's not quite the same yellow as when the wood burns, though, is it? A little paler, a little less orange. In fact, you can kind of compare them side by side if I'm lucky. Maybe not. That's the wood burning, isn't it? A little more orange. The barium was more of a pure yellow, I think. And the last one is calcium chloride, CaCl2.
We still have an extra one after that one.
Still one more box left.
Okay. That's our unknown.
Let's put our finger on it.
Calcium chloride, ready? Here we go. What do we get? Yeah, it's orange, red orange, I agree. A little redder orange than when the wood is burning by itself, I think, huh? A little more reddish. All right. You say there's one more row? Perfect. Unknown number 1 is what you put the label in there. Where it says compound, just put unknown number 1. I'm going to burn one more. I'm going to actually do this 2 or 3 times. And by looking at the color, go back to your list and you tell me what compound it was. Does that make sense? You look at the color, go back to the list, and then you can write down the chemical formula of it. Okay? I think these will work. These haven't soaked for quite as long. Should we come back to this, let them soak longer? Yeah, let's let these soak a little bit longer. Let's take a break from wearing goggles. Let's turn off the flame, and we'll continue the flame test for the unknowns in a minute. It is so hard to wear goggles with glasses. I get fogged up inside. Okay. So we'll come back and do the unknowns in a minute. I'd like to do 3 of them. We'll squeeze them into there somehow. Okay, so let's see. Our first one was lithium chloride. Its chemical formula, LiCl. And it is important what you capitalize and what you don't capitalize. Just like with your passwords when you log on to something, huh? Next, we have sodium chloride, which is the same as table salt. Salt you put in your food. But we use the symbol Na for sodium, which comes from the Latin word for sodium, which is natrium. Then we did potassium chloride. Potassium is just represented with 1 letter, just like hydrogen and oxygen and carbon, although most elements are labeled with 2 letters. Now for me, I'm going to make my 2 separate, and I'm going to make it smaller font. Make it like a 10 instead of a 14. Because properly, to show these formulas, you use a subscript. After strontium, we had copper chloride. And once again, that one has a 2 as a subscript. And the only way I can figure out how to do a subscript on here is by doing it as a separate little text box. Yeah, but I want to do it proper so you can see how it's supposed to be done, right? Yeah. If you just put a regular 2 afterwards, I'll be pretty happy. Barium chloride. And then we did what? Last one was calcium chloride. And we'll come back for the unknown in a few minutes. Okay, so the next thing, you should have written down all the flame colors that you observed, right? We had violet, we had red, we had orangish red, we had like all those colors, right? The next thing I want you to do is fill in the wavelength column. And the way you're going to do that is by going up to this chart. For instance, what did we say for lithium chloride? Red. So you pick a number, here's red, between 650 and 700. So I'm just going to go, oh, right in the middle of that was 675. So just pick a number that's kind of in the middle range, or if you thought it was like yellowish green, then go in between those, where they overlap. Does that make sense? If the red was a little more towards the purple, then you would pick a number that's closer to the purple. So you choose the wavelength that you're going to work with based on the colors that you observed and that chart up above. Fill this row, fill in this column for yourself.
It's like wireless would be like 380 something.
Violet. Well, I would still stay within those numbers. The pale was just because it wasn't as bright. It was less energetic, but it still had that wavelength. It was like amplitude, like volume versus pitch wavelength. You could have the same pitch either quiet or loud. You could have violet either bright or pale. I'm kind of just waiting for everybody to catch up. How are we doing at home? You guys ready to thumb up and let me know that you're here and all is good? How are you guys doing up there? You're good? Yeah. You got your colors and your wavelengths matched? Right? And you chose a single wavelength. You didn't write down all the range, right? Okay, so just make sure you chose a single one. Next thing we have to do is calculate. That means we have to do some math. You're going to need a calculator. We got to calculate the frequency. And we've done this before. If I give you the wavelength and I give you the velocity of light, we should already know that this is our wave equation, right? Velocity equals frequency times wavelength. But wait a minute, what do we know? We know wavelength, don't we? We also know velocity, so we need to find frequency, huh? So we have to isolate E equals F lambda. We have to use a little algebra. What am I going to do? I'm going to divide by F. Excuse me, I'm not going to do that. I'm going to divide by lambda, huh? Because I want to get F by itself. If I divide one side by lambda, of course I have to divide the other side by lambda, huh? Now I can cancel this. Do I have an equation for frequency? Velocity divided by whatever the wavelength was. Remember, wavelength is lambda. Okay? So the velocity is always going to be 3 times 10 to the 8th. What does that mean again? 3 with how many zeros behind it? Yeah. 5, 6, 7, 8. In other words, 300 million meters per second divided by whatever your wavelength was. Yeah. We have to divide now because we're using, we rearranged the equation. So we're always going to pop into our calculator, clear. Then 300 million. Make sure you put in 8 zeros. Divided by, the first one divided by 675, I get, yeah, look at that, what a cool number. 444,444. Good enough for me. We don't need all those decimals, huh? Okay? Now that's the number of vibrations per second. So imagine when we were looking at that reddish flame, it was vibrating 444,444 times per second. Isn't that crazy? You're always going to start by putting 300 million into your calculator and dividing by whatever wavelength you wrote down here. Okay? This is my actual answer for that one, yeah. 300 million divided by 675. Didn't you get 4444444? Uh-oh. Let me do it again. Make sure you have the right number of zeros. 3, 1, 2, 3, 4, 5, 6, 7, 8 zeros divided by 675 equals, I got it again. 444, comma, 444, dot, 444, for forever. You got it this time? That would do it, huh? So go ahead and fill out all the frequencies on your own. 300 million divided by whatever wavelength you had. Yeah, when you're done with your math, we're gonna test 3 unknowns. Hey, you guys at home, let me know when you're ready to move on. Give me a thumbs up when you're done with your math. Did you guys already add the unknowns at the bottom of the list? Awesome. You did that too, Alex?
750. For what?
Yeah, a lot. Well, a lot of it, I
You
mean.
got 750. I put 14.
Yeah,
That's why you should have gotten a higher.
Just tell me, how do I,
Yeah,
how do I
wait.
do these pages? How to do certain pages that I can look at.
This is Freddie.
What the hell?
Hello, Freddie. We're talking that so I put 410, and I got a less number than him because he got 750,000. I got this.
What did he put, 400?
Yeah.
I put 400.
Let's see, you have a smaller number and then a bigger number? Yeah, that's the way it should be. Remember, when one goes down, the other goes up? They're inverse. So if you had one that was smaller, then you should end up with the other one being bigger than him when you're comparing them.
It's a high number.
How we doing? You okay? Most comfortable place in the world, but I believe pretty soon we're gonna be filling up the rooms.
Dark red.
And I'm gonna rearrange the tables and such. So,
Put 620.
it's been great.
Well, I got a darker red.
I think we're gonna have more people in the building.
By the end of spring break, right?
I believe so.
You have to come every day.
They were talking about limiting it to 75% of capacity.
So how would that even work?
I don't know how it would work.
Every day?
75% every day?
Yeah. All right, let's do our three unknowns, shall we? Thanks, you guys, for responding at home.
Where are we putting the other two? Oh.
So, did you guys add the three, kind of squeeze them down here in the bottom? Did you add? All we have to do for the three unknowns is write down the color and then use that to identify the compound. Does that make sense? We're not going to fill in wavelength and stuff because we've already done that, huh? So basically, I've chosen three of these. I'm going to flame them again. You'll see the color, and from that, you work backwards to find out which one of these it is. Does that make sense? So once again, we got to goggle up. And I'm going to try to set this up so you guys at home can see. Yeah. Craven, we're waiting for you. Thank you. All right, I've already set the flame where we want it to be, huh? Unknown number one. Are you ready? Here we go. Get the color. Write that down for unknown number one. What color was that?
Green.
Yeah, kind of green, huh? And then use that to match it.
Is this one unknown number one?
That was unknown number one. It had a greenish color.
It's like blue going into green.
Yeah, we looked at it before, so it should be the same as one of the other flames we saw. All of these are just repeated. So then you just work backwards to figure out what molecule that was. What did you get?
Copper chloride.
Copper chloride. All you have to write down is the chemical formula CuCl2. All right, so you wrote down green and then you put CuCl2, right? Next one. Are you ready? Here we go. Looking? What do you get? Yeah, this one, it's starting to burn the wood a little bit, so ignore the orange. That was a violet flame before it started burning wood.
Violet?
Yeah, it would have worked better if it had soaked for longer in the solution. So then work backwards to figure out what was the chemical formula for that material. So by making observations, we can discover what something is, huh? We don't know what it is in the first place, but we compare it to things we already know about. We can figure out what they are. Last one. Here we go. Ready? Yeah, it's a bright red. It's a ruby red. Okay, you can take your goggles off, turn the lights back on. Okay, so again, on that last row, all you need is chemical formula and the color, correct? Yeah. Let's move on to the next page.
Fairly, I can't hear you.
Can't hear me. My microphone's on.
Lithium. Li.
We're not doing wavelength or frequency for the unknowns because we already did them for when we tested the same thing twice for those guys, right? So we already did them. Okay, so what's the main idea at the top of each page?
How can I analyze?
What's the main idea here? What does that say at the very top?
Elements.
Elements can be
Identified by the light they.
elements can be identified by the light they release. Did we just do that? Right? So here's a series of review questions for you. Okay? So you have this time to work on that. Ready, go.
Let's go easy. Let's go easy. What was that first one?
They're all chloride. All of them are what we call chloride salts. They're salts with chloride. Nice goggles, man. Usually they look so heavy. They're longer a little lighter.
Well, I guess I get to keep mine today.
Because you like wearing them so much. So you guys know we have class elections today. And if you're a sophomore, I think most of you are, you go to the small gym. If you're not, then look up at the board to figure out where to go.
Oh, I get to go to the cafeteria.
I don't want to go. I don't want to go to Reno because I have to work Sunday.
So we're not gonna do it.
No, it's because if my brother picks me up, they're gonna see me. Yeah, I think.
Hey, you guys, what do we call this piece of glassware? What do we call this kind of glassware? When it's
Beaker.
shaped like this, it is a,
Beaker.
this is a beaker, right? What about this one that we measure things with?
Beaker.
This is a beaker. You see how they're different? This is a graduated cylinder. Graduated because it shows measurements on it. Like when you graduate, you've been measured, right? A graduated cylinder. And then what about this one? No, this is a beaker. This is a flask. And its full name is named after this guy who designed it, Erlenmeyer. But if you call it a flask, I'll be happy. Erlenmeyer flask. Now look at this flask. Did you see this liquid before I put it in the flame test? Can you tell which one this is that's blue? Yeah, it is the copper.
Excuse the interruption. Just want to remind you that class meetings will start at 11:10 when the bell rings. Juniors will go to the large gym, sophomores to the small gym, freshmen to the theater, and seniors will be in the cafeteria. Those students who attend every day will go to their first period class or Mr. Resni's room. Students who are here on their virtual day will go to the small gym and see Mr. Christian. Thank you.
We should have voted for it.
Wait, so if you're here every day, you go to your first period.
Yeah?
I don't know. I'm sure I did. It's pretty simple.
Okay.
It might have been one number off from all of them.
Okay, well, so you turned it in?
Yeah, I turned it in before class. That's why.
Okay, I'll find it and I'll grade it and know what happened.
I was just off by one. Could I redo it? Because I'm not sure if I was, but.
I generally don't redo things like that because they're small assignments for one. And, you know, I usually put the answers on there. So if you want to double check it before I get to it, that would be better.
I'll stay confident.
All right, and we're done here for the day, you guys. So finish up page 4. That's basically your homework to finish page 4. Oh, what? Homework? Is this a new vocabulary word for you?
Yeah.
Well, it has 2 parts, home and work. Okay? Homework. See you later, guys.